The next strongest type of intermolecular force is what we call dipole-dipole, and that type of interaction, intermolecular force, exists between polar molecules. Now remember, in this picture we see this plus and the minus. This is really, it's not the same magnitude as a full charge. It's a partial positive and a partial negative. It's where the electron cloud is unevenly distributed across your molecule. And so what happens then in that case is we have a partial positive and a partial negative. So that's why these types of forces aren't as strong as the ion-ion, because the magnitude of the charge isn't as great. And so we have a partial positive attracting to a partial negative. So depending on, this is going to tell us that the strength depends on the polarity of the molecules. How polar is it? The higher the dipole moment, the stronger the interaction. And the dipole moment is going to depend on the extent of the delocalization of the electrons. All right. And you'll see that in this case we have, you know, the negative ends are going to be repelling each other, the positive ends are going to be attracting each other. So there's this kind of push-pull business going on with the dipole-dipole. In this case, this would be if it was in the liquid form. If it's in the solid, it's going to kind of arrange itself more so that the positives and the negatives are near each other and the like charges are away from each other. So this is the type of intermolecular force. It's weaker than ion-ion because the charges, the magnitude of the charges is less. It's not a full charge, it's a partial charge due to the unequal distribution of the electron cloud. Now the hydrogen bonding is a special type of dipole-dipole interaction. It occurs in compounds when you have extremely polar bonds, and that happens when you have a hydrogen bound to fluorine, nitrogen, or oxygen. And what happens there is, since the hydrogen only has one electron, that one electron is drawn, you know, very close to the oxygen, partial negative, partial positive. What it does is it leaves this hydrogen almost like a bare proton, okay? Almost like a full positive charge, because hydrogen itself only has one electron. And that's why we end up with an extreme polar situation when we have a hydrogen bound to an extremely electronegative atom, oxygen, nitrogen, or fluorine, the three most electronegative atoms. All right, and we've already seen the case in water. They actually draw like little dashed lines between the positive end of the water and the negative end of the water, indicating that that is a very strong force, and it's it's directionally dependent. Like the water molecules will orient themselves such that they can maximize the relationship between the negative and the positive. And that's why ice has such a unique structure. It can actually arranges itself with the attraction and the repulsion in such a way that the ice is actually less dense than the liquid, because the liquid's constantly rolling around, getting closer than is possible in the ice. And this chart here is kind of confusing if you first look at it, but what it is it's just showing some physical properties. Here's our first look at physical property, in this case boiling point, looking related to the different molecules. And this is molecules, hydrides formed from elements in period 2, period 3, period 4, and period 5. And you can see as you move across the period from carbon to nitrogen to fluorine to oxygen. Oxygen is actually next to the nitrogen. You can see that the boiling points are not what you would expect, whereas methane is all the way down here in the negative, around negative 170. Hydrogen or water is all the way up here around 100. And that's because these three molecules, even though they're about the same molecular weight as the methane, have much higher boiling points than the methane, because it is of the hydrogen bonding, and even higher boiling points than much heavier moving across the period, or excuse me, down the row, excuse me, down the column, water, and then there's hydrogen sulfide and hydrogen selenide. See how it's even all of these molecules have a lower boiling points than water, and you would expect them to be higher, because the trend is as you get bigger and bigger, heavier, all the other trends show that as you move down the group, the boiling points increase. Okay, but because of this extreme polar situation due to the hydrogen bonding, the force of attraction is much, much higher than would normally be predicted, because that the strong electronegative is pulling the one electron so far away from the hydrogen, it's almost like a bare proton. Okay, so we get unusual, very unusual properties when we have hydrogen bonding, not what one would predict at all.